Thank you. Good morning. I'd like to start by talking a little bit about ALPI. I'd be remiss not to, since we're sponsoring the event, so I'll just kind of go through this quickly, just give you an idea of who we are. We've been in the area for over 30 years, so we're an established company, and our focus is primarily in the area of software testing and everything that encompasses. Our client base is typically Defense Department and commercial clients. We focus a lot on automated test solutions, ways in which testing can be improved. We develop frameworks for automation to kind of simplify the implementation of those kinds of tools and technology into the software testing practice. We deliver ISTQB accredited software certification training to get folks trained and knowledgeable on a number of foundational topics on software testing, as well as topics like model-based testing. And we implement a variety of testing solutions around the DevSecOps solution. And finally, we support OSD on policy and guidance around software testing and test and evaluation. We have a local office here in the DC area, and my colleague Catherine is coming in today from our Boston location. So what are the challenges that we have in the area of software testing? Well, the first main challenge is really understanding the domain. What is it that we're trying to test, and making sure that we have the right information, complete information, deep enough knowledge, the right data, the right systems that we're trying to test. And that's always a big challenge for the test community. How do we make sure that we know what exactly we need to test, and what can we do to make that whole process better? The second challenge that we really face is around the rigor of the process itself. You may know what you need to test, but how rigorous is your process? How complete is it? What's your coverage, your test coverage? Are you covering enough of your system to really lower your deployment risk? What are the kinds of things that you need to do in an organization to really help you make sure that the testing process is broad, is deep, is complete, and really provides you kind of a strategy for success to make sure that you're not going to have problems once you deploy your software, your applications. And finally is the aspect about efficiency and effectiveness to the system. How do we make sure that even with a good software testing system, how do we make it efficient and effective? How do we make sure that it is fast, it is relevant? I think for many of you probably who have been involved in testing in the past, you know that if you take too long in testing, you might be forgotten, and they may say, you know what, we need to release the software. There's just no time. Nowadays, you see there's this radical shift from kind of siloed test teams to having a lot of the tests themselves be run as part of the pipelines in a DevOps and DevSecOps environment. So that kind of alleviates some of that, makes sure that those tests are run at the right time. But ultimately, we are always looking for ways to improve the efficiency and the effectiveness of how we do our testing. And that really leads us to why we're here, to talk about a particular approach of using model-based systems engineering in the area of model-based testing to improve the way we do software testing. And I'll pass it to my colleague Catherine to continue from here.
So basically, what is model-based testing? Our definition is it's an approach to testing that leverages MBSE to generate test artifacts and improve program integrity through enhanced test design and test execution. Essentially, you're providing the customer that surety that you didn't miss anything when you were testing. And using MBT provides a really thorough and effective, efficient verification and validation of the system. It enables that end-to-end traceability from your system through test and it identifies the gaps that you might have in requirements and coverage. So if you're just testing to textual requirements, if you forget to write a requirement, you're going to have capabilities that you might not test. So by having a model and mapping requirements into that model, you'll be able to visually see where you might be missing some coverage. And then finally, it establishes repeatability in testing and reduces maintenance costs. Because if you can just redo your test cases, if there's rework efficiently, then you'll save time on the back end. So there's 3 elements to model-based testing. There's the model, obviously. There's automated test design and test case generation. And then there's automated test execution. So it can be daunting to try to think about implementing all 3 aspects of these. So it just depends really on where your system is. So if you have a brand new system, then it makes sense to start with a system engineering and system modeling and go all the way through test. But if you're an existing program, you already maybe did your systems engineering, so maybe you just want to do the test, focus on the test piece and do test modeling and test execution. Or if your programs are already in production and maybe you're just running regression tests, well, then you can just do automated test execution of those regression tests. So it really just depends. It's meant to be flexible. So for the models, the system models represent the system, really the inner workings of the system. And it's informed by your stakeholder inputs, objectives, mission capabilities, requirements, any trade studies you might have done. Whereas test models represent the system from the test perspective. So not necessarily concerned about the inner workings, but more the inputs and the expected outputs. It can reuse the system model elements to keep that traceability, but you don't necessarily need all the details of the system. And the test models will also contain the verification architecture or any specific verification information you might need, like test approaches or specific test equipment for tests. And they both can contain requirements that can be linked to the various model elements as appropriate. So automated test design is when you're generating your test cases from the model. So ideally, you might have some tools that would evaluate the model and then generate test cases based on specific criteria that you would give it. So whether that's full coverage through the model or a random path through the model or least amount of test cases for a given amount of coverage. It can depend on what you provide. And then it also provides continuous testing and decision point evaluation, because if you develop, you can quickly create your test cases, evaluate those test cases, and circle back around and keep that continuity. And then on the bottom here in the corner, we just have some tool examples that will help you that have those capabilities and will help you achieve that. But again, it's understanding kind of the process first before the tools, as David mentioned earlier. And then automated test execution, of course, is executing your test cases, whether they have been created manually or automatically. And what you want to do ideally is run them on the system models and then also run it on the integrated system so that you can compare the results. So if you just generate your test cases from the system model and then rerun them on the system model, you're not necessarily going to find issues because those issues are baked in to your test cases. So having a test model gives you that test independence where you can then evaluate the design and evaluate the production. And again, some tool examples for test execution at the bottom. So to prove out this process, we created a just generic radar, and it has a system model that has two use cases, search and interrogation. And the system model has activity diagrams and requirements. And then there's the test model, which also has activity diagrams and requirements. And it reuses elements from the system model to keep that traceability. And then it also has function calls to the code, because essentially what we're going to do is perform software testing from test cases generated from a model. And then the third part is the software code of the model, the tactically representative code. So this is our search use case in the system model. And essentially, for our prototype, it is a radar. You're going to get a detection. You're going to calculate the signal-to-noise ratio. If it's above 9 dB, you're going to just double check. And if that's the first time that you're seeing this detection, you're going to go this path and send a validation check. You're going to check the signal-to-noise ratio again. And if you get above 9 again, you're going to eventually create the track and then send it over to interrogation. If at any point it's less than 9 dB, you're just going to ignore that detection. So this is that same use case just from a test model perspective. And the green is what I reused from the system model. But you can see that I added in some test information like VP for verification point, meaning a requirement is tied to that step, or just a generic test step. Function calls, depending on what path you go down, there are different parameters that you provide to the software. And so then this is the interrogation use case in the system model. Once you get the track, you can interrogate it either manually or automatically, and then you'll get the reply, and you'll decide based on that reply if it's a friend or a foe. And then same idea, this is the test model for that use case, and the same information with the green reuse, and the different function calls, and verification point versus test step with requirements tied in. And then if you go into one of those activities, you'll see kind of where this information is populated. So you'll have a documentation field that you can fill out. And all this information is meant to get pulled out and into your test case, so you can keep that traceability all the way through. So we'll see that once we create the test cases, we'll see this information appear. And then similarly, this is just showing where the code goes and the expected results for your test steps. So now that we have our model built, we can focus on the test design and execution. So what we're going to do is import the test model into a tool. We used MBT Suite. Then that tool creates your test cases based on the paths through your model. And then you can export those test cases into actual software code, and then that'll get run to evaluate your radar's software. So this is what the use cases look like in the MBT Suite tool. This is the search use case, and you'll see with the highlight yellow, that just means that it's a sub-diagram it highlights for you, so you can double-click that, and then the IFF use cases on the right there. And then this is where you plug in the strategies and how you want the tool to evaluate your model. So I did full path coverage, but you can also do guided path, shortest path, random path, just depends. And then there are different statistics that are calculated based on what you produce. So for my full path coverage, there were 6 test cases that were produced, 100% coverage, no requirements not reached, just various information you might find useful. So this is the first test case that got created. It's the ignore detection path, just straight through. And you can see this is where all this information came directly from the model. So you'll notice the verification point in test step, description, the expected results, and the code from that tag field, and then the requirement number tagged in. And then this is a second test case, just showing a different combination, a different path through the model. So this is the valid detection, manual mode, and it is a faux. So you'll see it's a little more in depth, but again, all the information is coming from the model. So then you want to take those tables and make them into code so that you can actually run them. We use Python for our example. And this is what happens. So the top box is your first test case, just ignore detection. So all you'd have is that one function call. But you'll see the requirement is pulled out, the expected result, the description, so you can keep that traceability. And then the bottom box is the second test case with the 3 different function calls. And then with the 6 test cases, you'll see the different combinations and the different paths you can go through. So this is just the code that's actually being tested. These are the 3 functions that we have, and that'll get run through with different parameters. So you then execute the test using whichever tool that you want. We just manually created the pass-fail, but the next step would then be automated analysis to evaluate your results. And I'll hand it back to Andrew for the challenges that we've seen.
Sure. Thanks, Catherine. So, first of all, well, we'll finish the presentation. We'll open it up for questions because I'm sure there's probably a lot of questions. Catherine kind of went deep down into some of the technical aspects of what's involved in actually implementing MBT in a testing environment. So what are some of the challenges? So one of the challenges is around the different tools. Catherine had a slide with different tools listed on there. They all have functionality. Functionality is important, but again, you need to find the functionality that's matches the particular requirements that you have, both in terms of functional requirements and also environmental requirements and what software you're allowed to run in your environment. Some of the tools are very capable and they'll actually be able to import any Cameo models that you already have. Some of them will not. The ones that don't, they basically have their own modeling environment, IDE, so you create your test model from there. So that's nice, that's great, but it also makes it a little more difficult if you're trying to derive something out of existing models. If your organization doesn't have models currently and you want to use model-based testing for your test activities to kind of give it a little more rigor, then there's a number of tools that give you that capability. The other thing that the tools do is the model-based testing tools help generate the actual code that can be then executed as part of your kind of end-to-end automated solution. So in Catherine's example, she showed Python code being generated based on the test conditions and the test design. The different tools can generate different code, but I also want to indicate that the way in which the tools generate code is not really the same as when you implement kind of a full-on automated framework for testing. Automated frameworks have a lot of built-in capability that can be integrated with other tools that can make it easier for non-technical folks to use the automation. Here we're talking about just generating a kind of a data dump of actual code that can be executed. So there is kind of a step from saying, okay, what can we do with this code? How can we implement the code that comes out of the tool into our existing automated framework? Or if we're building an automated framework, how do you do that? So there's some work to think about how you do that, because ultimately you want to make sure that people can understand and can use this effectively. The other aspect of the tools is some of the tools will generate just some very basic types of outputs. You have like different complexity paths that you can analyze through your code. You have data analysis techniques, combinatorial test techniques, pairwise test techniques, other techniques that can be applied to tools. Some of the tools have those built in, but if you're talking again about rigor of your test process and the definition of your data, you want to make sure that you capture some of that as part of the model-based testing process. Environments, depending on what your organization is, if you're in DoD, if you're in commercial environments, you may have some restrictions on what tools are approved to be used in those environments. In DoD, Cameo is a tool kind of that's widely used and widely approved for multiple environments. So if you can use that, that's great. Then there's some other tools. Catherine mentioned MB Suite is a tool that we've used. That's not widely used. It's kind of a smaller company that has some good functionality. That's why we chose it to do some of the prototyping that we do. And then there's plugins that you can build yourself to enhance the functionality of tools like Cameo or other tools. And then there's yet other tools that can help integrate different systems and the data that's coming from one system into another. So there's a number of different tools that really need to be considered here for this. And then finally, there's the issue of the AI-based applications that are now out there that we need to be testing. We need to think about how to test these, and we need to think about how do we test using model-based test techniques. How do we actually test an application that uses AI and machine learning? How do we apply the models in an effective manner in kind of this non-deterministic environment? So those are some of the challenges that are there that need to be considered, that need to be thought of. So to summarize, model-based testing, what can we say about it? Well, it's really a value-added way in which you can think about how you want to do your testing. It's something that allows you to think about testing end-to-end. What does that mean, to test end-to-end? That means that from your requirements at the very start to your test automation execution at the very end, that you have all of that kind of essentially linked together through definition of a model that derives your information, that allows you to do the test. So in doing so, what are you doing? You're actually helping the tester shift left. You're saying, let's move some of your test activity from the execution side, let's move it to the design side, do that up front, and guess what? Now we're going to have the tools derive those test cases for you, derive that test code, automation code for you, and do that automated execution. So it's like, let's spend the time up front, and then let's let the process kind of play itself out. And then when there's a change, we can make that change up front, and that change will kind of trickle through the whole process. So there's a lot of really good value in terms of what's out there, and it also helps the test community, T&E community, understand kind of how everything is linked together. And we are in a conference today talking about model-based systems engineering in practice. We wanted to give you a practical example of how we can use that in testing, and hopefully that's what we've done. So thank you very much, and we're open to any questions.
Okay, I have a question.
Sure.
So most of the time, architects like to design happy paths. So architecture is looking about how ideally our system should behave or should work. How your software tools, model-based testing toolkit addressing the misuse or abuse or any kind of other non-happy paths.
Right. So again, it's really not about the tool. It's really about how you define your test cases and your test data. And I mentioned earlier that one of the things that ALPI does is the ISTQB software testing certification training. And that is really came about because we realized that there's no established way to make sure people understand how to test effectively, how to test efficiently. There's no university that even offers a course in software testing, let alone a degree in software testing. So I like to say we're all kind of accidental testers. We kind of just stumbled into the field. So there's a lot of information out there through certification training, through other means, that really talks to, going beyond just that happy path, because the happy path will just get you your initial set of tests, but it's not going to do the edge testing. And as was mentioned earlier, the edge testing is really where the problems occur, when you're kind of beyond that initial happy path, and you need to kind of see how one software system interacts with another, and that's where things start breaking down. So.
If you mentioned this, I apologize, I didn't catch it. For the model-based testing, is it generally the same team of people, systems engineers, that are developing the initial system models, that are developing the test models? Because I could easily see program managers, project managers saying, well, clearly you know how to use this tool, you know this weird nomenclature with the arrows and stuff. You should be doing the model-based testing. Is there a general pattern or pros and cons, that sort of thing?
Sure. Do you want to address that?
Yeah, I think it probably just depends on what personnel you have on your program. If you only have one system engineer, one test engineer, it's easy for them to work together, or have the system engineer work with the test engineer to explain the models so that they understand it. Bigger programs, the big defense contractors, maybe they are distinctly separate, but you still need that communication between the two so that you can have that traceability and that the testers actually understand the system. So that's part of the whole shift left, make the testers work with the system engineers if they are separate people. But it probably just depends on the size of the company, the management understanding of model-based systems engineering and model-based testing, combination of the two.
Right. But the creation of the model, I guess, you're saying it depends.
Yeah, I would think so. Yeah, if all you have are system engineers, if that's in your culture that the system engineers test, they would create the test model, but they would need to understand that they have to switch their perspective now from the test perspective and not just
right, and that's
redo.
kind of my point, is now you're...
Right.
Yeah.
So ideally you want them separate but communicating with each other, but it would just depend.
Yeah. One other point to add to that is that some of the vendors in the model-based testing space, what they've done is they recognize that not everybody has the set of skills that the folks that are doing MBSE typically have. So their tools tend to scale down some of what's needed and just have the essential information needed for the test models without going into kind of a system model level of detail. So that is somewhat done in terms of how the tools are implemented. The other aspect of it is similar to like with test automation. When test automation first came out, the only people who knew how to use it were the folks who knew how to program, right? Because test automation is programming. And then what happened over the years is people started building what they called frameworks. And a framework was really a way to abstract the use of that tool, still have that capability, but allow people that are maybe not as technical, that didn't know the low-level programming, to understand how to leverage that technology. So what we're trying to do also with model-based testing is come up with a framework approach so that we don't have to have everybody understand all of the modeling, but look at it more from a perspective of an abstracted environment that you can feed the data and your parameters to, that will then actually do that execution for you, much like an automated framework would. Yes.
Yeah, as a follow-up to this question, actually, when you do model-based testing, as you mentioned, in some cases you have to separate teams, especially if you want to do independent verification and validation. And so I'm just curious in terms of recommendations, have you defined any guidance document, for instance, to say, do this model this way so that the communication with the IVNV team, which is siloed on purpose in this case, is made easier? Are there good practices, design patterns, recommendations? I mean, can you comment on this, please?
I mean, that's a great point. Right now, what we're doing is kind of more looking backward, is looking at existing models and giving recommendations for how they can be improved so that testing artifacts can be derived from them more easily. But ultimately, the guidance would be to kind of get more involved up front so that that is already incorporated as the system models are being created.